Our next speaker is J Junquera, who's going to talk about second principle simulations of counter-rotating vortice pairs in lead titanate, strontium titanate superlattices.
I am able to find where to plug it. Here, I found it. Okay. Working, thank you. So, can you hear me? Okay, thank you very much, Mr. Chairman, and thanks to all of you and the organizers for giving me the opportunity to present here our results on second principle simulations of counter-rotating vortices pairs in lead titanate, strontium titanate superlattices. So first of all, I would like to thank my collaborators, Pablo García Fernández and Fernando Gómez at the University of Cantabria in Spain, Jorge Íñiguez and our research student Mauro Gonçalves at the Luxembourg Institute of Science and Technology, Pablo Aguado Puente, who is now at the Queen's University at Belfast, and of course all the experimental help carried out by the group of Professor Rames and Elaine Martin at UC Berkeley. So one of the most important topics of this conference has been the domain walls. Domain walls are a very common understood object in the ferroid community, but it's not the only way how a spatially changing order parameter can arrange. Especially in the last few years, and coming from the ferromagnet community, there are more complex patterns for this order parameter where they can be arranged in skyrmion, merons, antimerons, etc. So, which kind of ferroelectric nanostructure develops depends critically on the relative magnitude of different energies that may involve magnetic anisotropy, spin-orbit interactions, exchange, presence of surfaces, interfaces, etc. So the question is, if in the magnet community, in the ferromagnets, we have all this rich behavior, can we do the same if we replace the spin degree of freedom by the electric dipole? So that's one of the main topics of this talk. So in this particular sense, lead titanate, strontium titanate superlattices is a very sensible material to look at. This is a fascinating material. Whatever you do in this system is interesting. The reason for this is that the very close competition between different orders here. So if we look at the bulk level, at the lead titanate, there are two phases that compete. One of them, two distortions. One of them is the ferroelectric distortion at gamma, and the other is the anti-ferrodistortive distortion. So at the bulk level, the ferroelectric distortion wins and inhibits the appearance of the second. Regarding strontium titanate, it's a quantum paraelectric and undergoes an anti-ferrodistortive phase transition at 105 Kelvin. When you put the two materials together in a superlattice, some of the symmetries are broken, and this very delicate balance between all of these order parameters may change. And completely new phases that do not appear at the bulk level may arise in these superlattices. Make predictions on this material is difficult because of several reasons. The first is a large spatial extension of the new phases, and the other is that the results are extremely sensitive to some external perturbations, such as the temperature, the periodicity of the superlattices, the electric field, the strain imposed by a given substrate, etc. So this, just the interplace of all these players here. Do I have a pointer? Mine is not. Okay, here it is. So the interplace of all of these may produce the appearance of phase competitions, order parameter coexistence, the emergence of new order topological parameters, and all of these effects can be found in these lead titanate, strontium titanate superlattices. So just an example about how the electrostatic coupling can be changed with the periodicity of the superlattices. So if we combine a ferroelectric and a dielectric material in one of these superlattices, any discontinuity in the out-of-plane component of the polarization at the interface between the ferroelectric and the dielectric may yield very large depolarizing fields that are energetically very costly. So if one way to just get rid of this penalty, electrostatic energy penalty, is that if we have a thin enough periodicity in the lead titanate, strontium titanate superlattices, the system may adapt a uniform polarization structure where here the out-of-plane component of the polarization is constant throughout the structure. So in this particular case, the ferroelectric layers are electrostatically coupled, and the price to pay for this is that we have to polarize the dielectric layer and somehow to reduce a little bit the polarization in the lead titanate. However, if we start to increase the number of layers of the dielectric, the energy that you have to pay to polarize strontium titanate increases, and at some point, you cannot afford it. And in that particular case, the system has to choose between revert to a paraelectric phase or just break in domains that are confined in the ferroelectric region that are now electrostatically decoupled. But these electrostatic degrees of freedom are not the only thing that are important in this system, because they are also prone to have a polarization rotation imposed by the in-plane lattice constant of the substrate. In particular, a compressive strain favors a 001 polarization, the so-called C phase, while a tensile strain favors an 110 polarization, the so-called AA phase, and in the middle, and very interestingly, in regions very close to the lattice constant of strontium titanate, there is a continuous phase transition, a continuous rotation between the C phase and the AA phase. So there is some tendency for the polarization to rotate. So a few years ago, we started to do some first principle calculations in this kind of lead titanate, strontium titanate superlattices, and essentially we were able to corroborate all these arguments. In particular, for a periodicity of 3 unit cells of lead titanate and 3 unit cells of strontium titanate, the ground state was monodomain, with the polarization pointing in this R phase, essentially along the 111 direction, while the domain structure here, we were able to stabilize the domain structure only as metastable phases. However, if we increase the number of unit cells from 3 to 6, then the domain structure becomes the most stable one, and they adopt here the shape of one of these domains of closure. So when the polarization goes from up to down, there is a continuous rotation of the polarization around 3 unit cells around the domain walls here. So this rotational pattern has been recently detected experimentally in this very nice image obtained using aberration-corrected transmission electron microscopy by the group of Rames, where these the so-called polar vortices are characterized here, but as spontaneous formation of laterally alternating clockwise and counterclockwise vortices of electric polarization. So these vortices are made bichiral, and that was one of the most important questions that we asked. So are they chiral and therefore optically active or not? The point is that we are at the limit of the things that we can do from first principles. In particular, this calculation here for 3 unit cells of lead titanate, 3 unit cells of strontium titanate, and 16 unit cells of periodicity for the domain includes of the order of 1,000 atoms, and it took more than 6 months to relax, single shot. So we cannot explore this kind of configurations in an easy way, and somehow we were forced to implement a new simulation method that we call second principles, and is already implemented in a code called scale-up. So what is the main goal of this second principle? So the goal is quite ambitious. So we want to simulate very large systems over 10 to the 4, 10 to the 5 atoms, including both the atomic and the electronic degrees of freedom, with an arbitrary high accuracy. Asymptotically, our accuracy is density functional theory. So everything at a modest computational cost and at operating conditions. That means at finite temperature, including time-dependent electric fields, defects, and so on and so forth. So this has been implemented in this code here. This is the web page if you want more information. So just a bird's-eye overview of the method. We are combining an accurate model potential to describe the lattice dynamics, and we include here all the possible modes of the materials, ferroelectric, antiferrodestructive, whatever, all of them. And on top of that, we have a tight binding-like approach to describe the relevant electronic degrees of freedom, and we have the cross-talking between the lattice degrees of freedom and the electronic degrees of freedom. So we have all kind of electron-phonon interactions. So we call it second principles because we don't have any input from the experiment. So all the parameters are taken from first principle simulations on smaller systems. And despite everything has already implemented, I have to say that in this work, we play only with the lattice part. So all our systems are insulating, and therefore, we are not using the electronic capabilities in this study. So we can do now several things using this second principles technology on these lead titanate, strontium titanate superlattices, such as the emergence of chirality in these polar vortex superlattices, or the coexistence of phases of Pavel skyrmions. So due to time constraints, I will focus only in this talk in this first part. So if you are willing to get more information, we can discuss the other two at the coffee break. So we have carried out second principle simulations on lead titanate, strontium titanate, with 10 unit cells of each. And here you have some of the results we are getting. So here the arrows point the components of the polarization in the plane of the screen, and the colors are the component of the polarization perpendicular to the plane of the screen. So green pointing inwards, magenta pointing towards you. So we could identify different atomic geometries that were very close in energy. In particular, the three that I am plotting here are degenerated in energy. So we do observe a continuous rotation of the local dipoles with pairs of clockwise and counterclockwise rotations as before, but superimposed to this structure, we were able to detect a component of the polarization pointing in the perpendicular direction of the screen, so in the direction of the axis of the vortices. So the fact that we have this component of the polarization here at the domain walls suggests that the domain walls themselves are ferroelectric. And this is a result that has been previously obtained, for instance, by Jacek Wogdel and Jorge Iñiguez in 180-degree domains in bulk lead titanate. So they were able to observe that the domain walls themselves were able to sustain a component of the polarization. Also, there was detected by the group of Hlinka, where they were able to detect a very rich structure phase diagram predicted in these 111 barium titanate domains, and many works by Salge. So it's very well established now that the domain walls themselves may be ferroelectric. So here, the domain walls show a mixed easing, so the polarization going from up to down, mixed with null, so this rotation of the polarization in the plane of the screen, combined also with some block components where the polarization is just going out of the screen and coming back to it. So it's a mixture of the three of them. And the fact that we have also this axial component of the polarization makes the structures chiral. So we can take, for instance, one of them here, and this is the original one, the one that is here surrounded by this orange square here, and we can see how, and we are taking three reflections, three mirror reflections. One is this, another one is this, and another one is this. So we can see how the reflected images all map onto the other, but we cannot map any of the reflected images into the original one, just doing rotations or translations. So the structures with this axial component of the polarizations are chiral. And we can define a hand for all of them. So to do this, just take your right hand and then curl the fingers in the direction of the arrows. And then if your thumb is pointing in the same direction as the axial component, then the vortex is right-handed. If not, it's left-handed. So making this trick, we can see how the two vortices here are right-handed, the two vortices here are left-handed, and here in the middle I have one that is left and another one that is right. So we can say that we have here two structures that are chiral enantiomers, this one and this one, while the center one is achiral. So just to put some math on this, we can define the helicity. And the helicity is defined as the integral over the whole volume of the dot product of the local polarization times the curl of the polarization here. So since this polarization tends to measure the rotation of the dipole, we expect that the helicity density, the integrand of this, will be localized at the position of the vortices. So just taking this equation and computing it, the helicity density, we can see how the here the right-hand structure displays a positive helicity, the left-handed displays a negative helicity, while the achiral structure has a helicity that vanishes, essentially. So in the last couple of minutes, so that's the theoretical predictions. The fingerprint for chirality is would be that a different answer, a different reaction of the system under different circularly polarized light, left or right-handed. And this was precisely the experiment that was carried out in the group of Professor Rames at the University of Berkeley, where they were using soft X-ray diffraction. So soft X-ray, because of three reasons. First, the wavelength of the soft X-ray is well matched with the periodicity of the vortex, anti-vortex, or clockwise, counterclockwise vortices. The energy of the soft X-ray is very well matched with this resonant transition between the titanium 2P and the titanium 3D. So we can directly probe the anisotropic electronic structure of the titanium 06 octahedra, and we enhance the scattering cross-section. So essentially here, what we have is, okay, those are the typical spots obtained from the XRD experiment. And if we look at one of these spots, and we look at them in detail, we can detect the presence of satellites here that are the signature of a superlattice, of a superstructure with the clockwise, counterclockwise vortices. And if we perform here a cut, a horizontal cut, and plot the intensity of the diffract X-rays, we can see two things. First, the appearance of the satellites with lateral periods that matches very well with the counter-rotated vortex pairs. But second, that the intensity of the diffraction peaks are markedly different for circularly polarized incoming X-rays with opposite left and right-handed helicity, with differences that may be up to 20%. So this is a clear indication of X-ray circular dichroism that is the fingerprint for chirality in the system. So just the last slide. So the origin for this chirality can be traced back to the presence of a helical structure here at the center of the clockwise, counterclockwise vortices. So if we just plot a line here and look at how the polarization is changing, we can see how we have an helical structure. So the diffracted beams with a positive lateral component of Q sends a clockwise or counterclockwise helical rotation of the polarization, and therefore interacts much better with the left-handed polarized light, while the Q lateral positive sense a clockwise helical rotation of the polarization, so they interact much better with the right-handed polarization. So essentially, this is the take-home message. I think I ran out of time, so I leave the take-home message here, and I'm ready to take your questions. Thank you.
We have time for some questions. Okay, microphone, please.
Could you please show the diffraction patterns a few slides ago, just towards the end?
This one?
And the next one was electron diffraction. Okay.
This or this?
Okay. Oh, thank you.
Anything else? So I have a question. It seems that the nature of the domain walls matters a lot in terms of whether you can have an Ising-like or a nail-like or a block-like wall and the mixture of those to get a vortex state. So is this general for a tetragonal ferroelectric, or can this live in a rhombohedral ferroelectric or orthorhombic ferroelectric where you might have more possible domain states to relax into?
Yeah, I think my experience is that the structure should have a tendency to show, well, of course, polarization up-down, but also to show the tendency for a polarization rotation. So in this particular sense, systems with a polarization along the 1-1-1 direction would be very good candidates to show the emergence of the three components at the domain wall. You have up, down, but then at the same time you have to go out of the plane of the screen, entering again, and for that it's very likely that if you have a system that shows somehow a tendency to have already a polarization along the three directions, that would be perfect.
Thanks. Oh, one more?
Yes, thank you. Hi, I really enjoyed your talk. I think you made the argument that these flux closure domains and vortices are related to the length scale of heterostructure patterning in materials. What is the current status in your mind of the quest for finding vortices in materials where the underlying atomic and compositional structure is bulk?
And can we have the next speaker comment too, please?
Yes. If you have no compositional layering or no thin film behavior, will it also be possible to find vortex states, or is it required to have spatial confinement to have vortices?
No, it's not required to have a different. It's not required to have a different compositions in the system. In particular, we have some preliminary results on lead titanate, pure lead titanate, related with strontium titanate, where you can induce locally a domain pointing down inside a matrix pointing up, and it's, let's say, automatically the system displays one skirmion-like structure. I mean, just the system wants to close the up-down domains, just forming this kind of closing pattern, and this is just for a single material, no need for two different materials. Of course, this will be metastable, because if you have lead titanate, whoop, everything will tend to polarize in a given direction. But at least you can stabilize them at a metastable level.
I think with that we have to move on for interest of time, but we can talk in the coffee break. So thank you very much.